it's my pleasure to introduce to you Aida Nematzadeh. I pronounce correctly. Yes. And she has a PhD in computer science from the University of Toronto in Canada, where she was working. The thesis was about computational modeling of word learning and the role of cognitive processes. And now she's a postdoctoral research associate at UC Berkeley with Tom Griffiths, and she will talk about language learning and representation in human computers. Please, thank you very much.
Thank you. Thanks everybody for coming. Today, as you just heard about the title, I will be talking about language learning and representation in humans and computers. So let's look at children at the beginning. So when children start learning their language, they face a very challenging problem. They hear utterances, something like "boz, bazi, mikonad," while they are looking at their environment. But they don't understand anything about this utterance. They really don't know anything about the words or structure of the language. But soon after a short time, they're actually able to recognize the meaning of the individual words. So in this case, "boz" refers to the goat that you're looking at. And shortly after that, they're actually able to understand the meaning of the whole sentence. So here, the goat is playing. This is still a very challenging problem for the artificial intelligence systems. And artificial intelligence systems are still far from human performance in many language tasks. So why is it, actually let's look at an example of how...
Somebody is drinking champagne.
Cheers.
We're very celebratory.
That's great. Well, let's look at an example of how the artificial intelligence systems perform in language tasks. I'm showing you here an example from the web interface of Google Translate, and I took the previous sentence. I didn't really try to pick a good example, actually, and copied it in the translation box. So it's saying the goat is playing, and the translation is in Farsi, but if I translate it back to English, it's actually saying the goat is streaming. So it seems here that the translation algorithm is actually confusing the sense of play as playing games with the sense of play as playing music. And more interestingly, if I take the Farsi sentence and put it back in the translation box, it's actually translating it to pork is playing. And I don't understand how this mistake is actually happening. But my point here is that the AI systems currently are still far from human performance in many language tasks. So why is it that we are very good at language learning? Or what is it about people that is unique and makes us very good at learning languages? In my research, I study this question. I take a computational approach to study language learning. More specifically, I'm interested in studying various aspects of language learning that might be unique to human experience. For example, what is the role of general cognitive processes such as statistical learning, memory, and attention in learning the language, as opposed to a language-specific mechanism? So is it because we are equipped with a specific mechanism for learning languages that we are able to learn a language, or is it because of our general cognitive abilities? The other area that I'm interested in is what is the role of innate versus learned biases. And by biases, I mean any prior knowledge about language learning or the structured assumption about the environment. Another area that I'm very interested in is what is the role of appropriate representation. Many of our cognitive abilities in language processing depends on how we actually represent the linguistic knowledge. And because, for example, the way that we're able to identify relations among words, similarities among words, depends on how we represent these word meanings. So this is another area that I'm very interested in. Another question that I'm interested in is to use the lessons learned from these studies to improve the current AI systems. So can we use what we learned from studying humans and make better AI systems? So in this talk, I want to focus on the role of appropriate representation of semantic knowledge. And by semantic knowledge, I refer to our knowledge of knowing that a word label such as cat refers to something like the picture you're looking at, which is actually my cat. And the word such as dog refers to other picture that you're looking at, the picture of a Great Pyrenees. And so given these word representations, it's not that we're just able to represent these words, we're actually represent them in a way that we're able to identify semantic relations among these words. So we're able to say that cat and dog are semantically similar, and cat and milk are semantically related because they occur in the same scenarios or in similar contexts. And this representation, the overall representation of the semantic knowledge, is very important in a way that we are able to perform search and retrieve information on this knowledge. And let's just, so this will be something I will be talking about more during my talk, but let's just look at two examples. Like we're looking at two types of representation of semantic knowledge, two semantic networks that have the same number of nodes and the same number of edges. One of them is more sparse, and the other one is more, I guess, messy in a way that the edges are all over the place. So there's no structure in it. And we know that doing search and retrieving information on these two different networks is very different from each other. Again, my point here is that representation of semantic knowledge kind of determines how we actually use this semantic knowledge, and is very important in both computers and people. In the first part of the talk, I want to focus on the role of semantic representation in people. So there are two questions that we can ask when we think about people. How do we actually learn to represent a word, or do we learn the word meanings? And how we can actually represent the semantic relations among the words in a way that actually allows us to use this semantic knowledge. And again, for computers, we have similar questions. What is the rate of representation to capture different aspects of similarity that people are actually able to judge? So the first area, the first part of my talk, is an example where we actually use what we know from computer science, machine learning, and statistical learning to learn something about cognitive science of language learning, or how people learn and represent language. And the second area is the other direction. It's basically where we look at how people learn languages, the cognitive science of language learning, to inform or learn something about artificial intelligence systems. So let's focus on semantic knowledge in people, or how people actually learn to represent each word meaning with a picture subject, something like the cat you're looking at, and also learn the relations at the same time. The first question I want to talk about is how we actually represent word meanings, how we learn individual meaning for every word. A very general mechanism for learning word meanings is what is referred to as cross-situational word learning. This is this idea that people are very sensitive to the statistical regularities across different situations. So if I show you one picture like the dog here, and I refer to it as a dox, you probably have some idea what the dox is, but you're not maybe too sure. If I show you another example and say, look at the dox, you probably know what the dox is, and in this example is the dog. So the question is how much we can learn if we apply this algorithm, if we computationally implement this algorithm and apply it to word learning input. And is it possible to actually represent word meanings in a reasonable way? Before talking about the algorithm, I need to tell you about how we can actually represent word learning input. So when children are learning a language, what they hear is utterances from caregivers and parents while observing their environment. So we need to represent both of these sets of inputs. To represent utterances, we actually use a corpora called child. So it provides us with utterances from caregivers and parents, and basically what they are told, what they utter to kids, or what the children are hearing when they are observing their environments. But we also need to come up with a scene representation for these utterances, which basically is the environment of the child while they're observing or hearing their utterances. To do that, we create a gold standard lexicon. In this lexicon, for every word, we have a ground truth meaning, so we know a set of semantic features with their probabilities to represent every word in our data. And using this gold standard lexicon, we are able to actually generate a scene representation. So given an utterance, which is a set of words, we holistically sample features from the gold standard meaning of every word in that utterance, and we represent each C as a set of semantic features. The word learning problem, given this input, an utterance, and a C, now is what is the right features for a given word. So for the word milk in this example, which of the features in the C are actually part of its meaning. And then the output of our model, what we're interested to learn again, is a representation for each word meaning, which is, in our case, a probability distribution over all the semantic features. So we know how likely each feature is for a given word. And then at the very beginning, we assume that all the features are equally likely. So we assume the model has no knowledge, no linguistic knowledge of the language. So can we implement the cross-situational learning that I just explained to you, given this formalism? So The problem at the beginning is that we have a set of utterances and a set of features, and we're interested to map these features to words or align these features to words. And at the very beginning, so this is the main representation of the word milk. All the features are equally likely, so all the alignments are equally weighted. But using this weighted alignments, we can actually update what the model knows. So the second, now we have a word main representation for the word milk, which reflects the features that the model has observed with this word. And then the second time we actually see an utterance with the word milk, we use the per-learned meaning to update, to calculate the alignments. And now alignments are actually weighted such that the features that occurred before with the word milk are actually more strongly associated with it. And then we repeat this process and again update what the model knows. So this example is very similar to a task that we do computationally, which is the machine translation task. So we are basically translating one sentence to another sentence. Here we're translating one sentence to the semantic features that are in the environment. More mathematically, we can basically formalize what I just explained to you in 2 steps. The first step is that we are interested in calculating probabilities for alignments, which we do using this formula. In the numerator here, we're simply looking at the strengths of association between a feature and a word using the learned meaning. So the probability distribution that the model has learned for a given word. And in the denominator, we're introducing a sort of competition among words. So we're normalizing this association over all the words in the utterance. So basically now every feature can be only strongly associated to a few words. And then using this alignment, we want to update the knowledge of the model of all the words to the meaning probability. So the meaning probability here, again, is a normalization of the overall association score. So in the numerator here, we are looking at how likely it is to see a feature in a word, given all the alignments that we have calculated so far, not just one input, everything that the model has observed so far. And then we again normalize this to get a distribution, and this normalization introduced a set of competitions among features. So now we are saying that for every word, there are only a few features that are strongly associated to it. And this process is repeated for every input pair. And this algorithm that I just explained to you is an incremental version of the expectation maximization algorithm for in-frame the parameter that we're interested in, here the meaning probability. So far what I told you allows us to learn a representation such as what we saw in the previous slide for every word. But another important part of semantic knowledge is actually how we can learn the relations among words and what is the representation of the overall knowledge, such that it facilitates search and retrieval and the use of semantic knowledge. Previous research shows that there is this interplay or trade-off between the structure of the representation and the complexity of the search algorithm. So if you have a simple representation where we only know the meaning of the words, as what you're looking at here, in order to basically predict or replicate search behavior in people, we need to do a strategic search algorithm, which not only uses the similarity of the words in making a decision, so it has 2 stages, but it also uses the global frequency of the words. On the other hand, if we have a structured representation, something like what you're looking at here, where we're actually thinking about the relations among the words at the same time, basically the semantic network, we can do a very simple search algorithm, a random walk, to predict the same behavior. So what it shows us is there's this clear interplay between the structure of the representation and the complexity of the search algorithm. But the question that I want to talk to you about is basically whether we're able to learn this structured representation such that a simple search algorithm would be enough in predicting human behavior. And why are we interested in simplifying search? Because retrieving information is something that we do frequently. We learn a structured representation once, but we want to use this information frequently in our everyday activities. So cognitively, we are interested to reduce the cost of search. So let's talk about how you can actually grow a semantic network. The challenging problem here is whenever we learn a word meaning, whenever we are exposed to an instance of the word, we need to, if we are growing the semantic network, we need to update all the edges in the semantic network. We need to compute all the purpose similarities between the given words such as panda with all the words in our lexicon, which is very expensive. So we want to avoid this computational cost. What we propose here is instead of looking at all the words in our lexicon, we can think about a smart way to select a subset of words. So select words that are potentially similar to the word we're interested in. The reason here is that basically given our lexicon, and a new word, a panda that we are learning, or the meaning of the word is being updated, not many of the words in our lexicon are actually going to be similar to the word. So we are not expected to have a lot of connections from the word panda to the network. If we are able to find words that are more similar to the word panda and just compare those words with this word, that is enough. So all we need to do is to come up with a way to select these potentially similar words. And we do that by incrementally forming semantic clusters using the current meaning of a word. As you can see here, at each stage of the learning, the model uses the current meaning of the word panda, or any word, to add it to one of the existing clusters or to a new cluster. And then after clustering each word, we use a subset of words by looking at the similarity of all the clusters to the word. So instead of comparing all the words to a given word, we only compare the clusters to a given word. And we only select the words from the clusters based on the similarity of each cluster to the word. The more similar the cluster is to the words, we select more words from that cluster. So by this algorithm so far, we are able to learn a representation for a word, and we are able to learn the connections of a semantic network. How do we know that the semantic network is actually a good network and is something that approximates semantic knowledge of people? We need to evaluate the semantic network with three respects: the structure of the network, whether it captures the semantic similarities we are interested in, and whether we are actually able to perform the search behavior on the network. So let's look at the network's structure to begin with. Previous research shows that the semantic network of adults has this specific structure referred to as small word structure, which I probably should not explain here, but I will briefly mention. So basically all it means that it's a sparse network, so there are not many edges. It has highly connected local subnetworks, something like what you're looking at here. And because of these highly connected subnetworks, there are nodes that are high degree in the network and makes these subnetworks connected to each other. So although there are not many edges in the network is highly connected. And to measure whether a network actually has a small word structure, it's often compared with a random network. So this is the equivalent random network for the network you're looking at over there. And the random network is created simply by randomly rearranging the edges in the actual network. So we are interested to have a network that is highly connected, similar to the random network, but has these local subnetworks, so these islands, as opposed to the random network.
Can I just ask a quick question? Sure. So is the network based on like people's associations? So is it actually experimentally tested, or is that from a thesaurus type of data set?
So this is what we grow using what I just explained to you. So this is the results from our model.
Oh, okay.
We create this model network. This is actually the results from our algorithm. And then for this specific grown network, we create a random network that is corresponding to the grown network.
So when you say it reflects adult knowledge, it's based on that, on your algorithm, but not...
Oh, so the statement above there is from previous work. They actually looked at different sources of knowledge. So one of them was thesaurus, one of them is word association norms, and also a dictionary type of lexicon. And they observed that in all these different types of resources, they basically see networks that exhibit a small word structure. So that's from previous work, yeah. Sure.
How exactly edges that you find?
So say that again?
How exactly edges that you find?
How are the edges defined? Oh, so basically for every word pair, we look at the similarity of them using cosine. Okay. And then if it's higher than a threshold, we say there's an edge.
So it's a function of threshold.
Yes. Yes. Okay, so we looked at three ways of creating a network. One was what I just told you about. We also looked at one baseline and the best results that we could get. So the best results is when we compare all the words together at every point in learning, instead of selecting a small subset. The random method is where we only look at words, but we select them randomly instead of using what I just explained. And the cluster context is using the information in the clusters that I showed you, and also looking at the context of a word, so words that partner with a given word. We see that the networks that we create with the cluster plus context approach actually exhibit a small word structure. However, the random method, in the random method, only less than 5% of the networks actually exhibit a small word structure, 2% of the networks to be exact. And then the upper bound approach, not surprisingly, actually exhibit a small word structure. And then we also looked at the semantic connections of these networks and compared them with adult similarity judgments. And we see that the cluster plus context is the best approach for basically predicting the semantic connectivity of the relations. Yes?
So you're comparing the word pairs based on the latent feature model you talked about in the very beginning, the words and utterances associations, or how are words compared?
So for every word we have a representation, a vector representation, which we learn using the algorithm that I told you.
The association one. I see, and that's how you, and then you're doing the cosine similarity of
Yes.
those? I see, yes. And now, how long is that feature vector?
So
What's the
really,
cardinality of it?
so it's something between 100 to 200. So it depends on the number of features in the input, because we learn a distribution over all the features for every word. And some of these features have very low probability because they're
You
not.
regularize it?
You mean
Use some kind of regularization?
So it's a probability distribution, so it's normalized, but we don't regularize it in a sense that it's
When you
not.
learn the parameters, I mean.
When we learn the parameters, so what parameters? The meaning probability? No, it's just a smooth probability. I mean, there's no regularization in the sense of machine learning regularization, but there is a smoothing parameter for unseen features. Is that what you're asking?
But wouldn't that make sense? Because if there is a feature that's contributing very, very low, it doesn't matter whether it sums to 1, if it's a feature that's contributing a very low amount. As in, like, I guess you're treating it like a topic model.
Not really. It's more like vector space representation, but for every features, you assume some very small probability unless you see it frequently with the word. Does that answer your question?
I'm just trying to see if the edges would actually make sense.
Oh, so think of the edges as semantic similarity between the words.
Depends on threshold. So, or just threshold.
Right. So for selecting a threshold, we actually compare this with the gold standard similarities. So we want to put a threshold. So actually, it's interesting because depending on how fine grains you want to get clusters, you can vary the thresholds. Higher than some threshold, it makes sense. You actually get the basic level similarities. If you use very high similarity thresholds, you end up with very fine grained clusters. For example, different types of dogs. But it seems that like the way we select the threshold is basically having the right number of relations compared to gold standard or gold standard evaluation data.
So let me ask my question a different way. When you're trying to find your parameters, are you doing maximum likelihood or are you doing maximum opposite?
It's maximum likelihood is the EM algorithm.
I see. So there's no prior that you're using?
So you can think of the smoothing parameter as a Dirichlet prior.
I see.
So that's the only prior knowledge that the model has.
I see. And then what is the context over there? The cluster plus context?
Oh, the context is the words that quarter in a window close to the given word. So when you're processing the utterance size, the window of the neighbors of the word.
I see. So far I have two free parameters, right? The threshold and the window size for the context.
Right, we actually didn't really try varying the window size. It seems that the only changes that it makes from other experiments that we've done is whether you're like learning semantic relations or syntactic relations. And we just picked 5, which is typically used for semantic clusters.
Let's perhaps
Sorry.
the question later so
Right.
that let
Yeah,
them finish.
sorry. In
And then
computer science we ask questions.
we have
as
ample
go.
time, we have ample time of discussion so
Okay.
that we don't.
Okay, actually, I'm not sure how much time I have at this point, so let me know if I need to stop or skip things. Alright, so the other aspect that we were interested in was whether the semantic network enable us to do a search, simple search, and predict human behavior. A set of experiments that typically is used for understanding semantic search in people is this task, which is referred to as the free recall task. So basically, people are asked to produce, for example, name animals as much as they can in a limited amount of time. So in this example, in 3 minutes. And they start producing words such as dog, cat, lion, and zebra. And if you look at the words that they produce, it is actually interesting because they form semantic clusters or patches. So dog and cats are pets, and lion and zebra are African animals. So what it shows this data is basically that when people are thinking about words, it seems that they're actually exploring one semantic cluster and producing words from that semantic clusters before switching to another cluster. And interestingly, if we look at the time they take, this is data from Hills et al. So this is data from human participants, and we're looking at the retrieval time and the y-axis. So the time that people take to produce words in one cluster, so these are words that are produced between a cluster, and this is the cluster switch. The time that people take to produce words after the switch is much larger than the average retrieval time. So that which again shows that people are searching for words in a cluster that are semantically similar, easier to retrieve, and then switching to a different cluster takes more time. So what we wanted to see was if we have the semantic network that I showed you before, and if we do a random walk on that network, can we actually replicate the same pattern? And we actually do replicate the same pattern. So this is the data from our model, and you can see that again, the cluster switch happens when the retrieval time is greater than the average retrieval time. And then we also just see that there is the time that people take to produce words within one cluster is less than the switch. All right. So I want to sum up this part. So far I talked to you about how we can actually grow a semantic network that represents adult knowledge. And I showed you that we can do this with using a limited number of computations. And also that it seems that very important to use the information abstract clusters and also the context of the word to grow these semantic networks. And then given a semantic network is structured representation, we can simplify the search algorithm. So now I want to focus on semantic representation in people and basically talk to you about what is the representation for capturing different types of similarity that people are able to judge. So for example, we're able to say that again, cat and milk are similar because they are carrying a similar context, and lion and cat are similar because they look like each other maybe, and lion and zebra both are African animals. The very well-known approach in computer science for representing words is what is referred to as the vector space models. The idea here is that we represent every word as a point in an n-dimensional space or as a vector. And given this approach, we are able to learn representation for individual words. But learning semantic relations is usually simplified to learning to the distance between these two vectors. So it's either the Euclidean space, sometimes it's the cosine of the angle between these two vectors. And this approach has been very successful in many applications, such as word similarity, semantic role labeling, and so on. And very recently, two models, namely Word2Vec and GloVe, actually improved the performance of these models by being able to be trained on very large corpus, something around 100 billion words. And they produce a large coverage or large vocabulary size, so those are really great for the applications that I just told you about. But today I want to talk to you, I want to focus on one of the shortcomings of the vector space representation, which is basically seems to be inherent in the way we think about word representations when we think about vectors. So this idea of having the geometric constraints of the Euclidean spaces and basically the vector space representations are subject to these geometric constraints. So for example, when we think about distance as asymmetry, when we think about similarity as distance, we are not able to actually capture the asymmetry that we see in human similarity judgments. So we know that if you tell people the word text, they would say the word that they can think of is the word book, but the other direction is not correct. If you tell them the word book, they will think of the word read. Similarly, if you tell them the word cobra, they will think of the word snake, but the other direction is not correct. Another interesting pattern is what is referred to as the triangle inequality. So let's look at an example here. If you think about relations among more than one word pair, so when we have, let's say, 3 words in this example, there are often cases where 2 of the pairs, words in 2 of the pairs are very similar. So here, bolt and asterisk are similar, bolt and buckle are very similar, but asterisk and buckle are not similar. And if you have vectors in the Euclidean space, you need to obey the triangle inequality. So the distance between asterisk and buckle cannot be larger than some number. So what it shows is that maybe there's something inherently probabilistic with representing words in a vector space. And I want to show you whether these newer models that are able to predict a lot of different types of similarity able to actually capture these shortcomings. So what we did is we take this data set, which is a set of association norms, Nelson association norms. So this data set is collected by asking people to produce words for a given cue. So for a given word such as table, we'll start producing something like chair, cloth, eat, and the probability here is the number of participants who actually produce each word given a cue. So if you look at parts of this data set, it's actually a semantic network again. So we see that like people are representing the relations among the words in a way that we can convert it to a semantic network. Another thing we needed to figure out was that when we look at distance measure, like cosine, the similarity is symmetric, and the data that people actually produce is asymmetric by nature. So instead of using a symmetric measure such as cosine, we're actually looking at conditional probability, where we basically normalize the similarity of two words given all the words in our data. In doing that, we're interested to see if the current models actually replicate trying an inequality. So to measure that, or to evaluate that, we look at all the word tuples. So when we have three words as these examples, where the two of the edges, two of the pairs are highly similar. So that threshold is a high threshold. And then we plot the distribution of the other similarity, the similarity of the words in the third pair. If we look at our gold standard data, the Nelson association norms, we see that for even very high thresholds, so this is the number of pairs we see for the that are actually, where we're looking at the distribution of the word, given word line, and for very high thresholds, we see that there are a lot of pairs that have similarity close to 0. So it shows that this triune inequality actually is an issue in our gold standard data. When we try to actually replicate this with glove and word2vec with both of them, we don't see that pattern. So we don't replicate that distribution. We see a distribution which is more similar to normal. So even for very high similarity threshold, most of the pairs, if the words in the third pair have similarity close to the other pairs, so we are not able to see this small similarity in our data. All right, so to sum up this part, I wanted to focus that the prior vector-space representations are very good at capturing oral association given very large amounts of data, but they fail at predicting relations among more than one word pair. And it suggests that maybe we should actually think about models or approaches that think about modeling these relations between more than one word pair more directly to be able to actually predict the behavior we see in people. So, and this is the summary of what I've told you so far, the importance of representing semantic knowledge in people and computers. Now I want to focus how much time do I have? Okay. I want to focus on what I'm excited to work on and what are the possible future directions. So the questions that would basically guide my research again are these two questions. How do we learn a language and how can this inform AI systems? One area that I'm very excited about is the role of deep representations. By deep representations, I mean the representations that deep neural networks learn. So we know that these models are very good at representational learning. There are previous work, for example, they can show that deep representation are able to predict typicality rating. For example, that this is a less typical pillow than the other picture. And also, they are very good at measuring similarity judgments in people. So these two animals are less similar than to like a tiger and a lion. But these representations are not really explored in terms of how they perform for language tasks. And that's one area that I want to focus on. And we can actually think of very different ways to study this. One is in thinking about how these representations predict formal languages. And formal languages are interesting in studying language because first of all, we know that like English can be formalized with context-sensitive and context-free grammars. And we also know that like this grammars show how expressive a model is. So like just studying if the representations are able to predict these languages, we get a sense of how expressive they are. And the other area that I'm very excited about is if we can actually model compositionality. One important aspect of language learning is that it's a compositional phenomenon. So we are able to combine word meanings and make a phrase that has a different meaning. And then whether we are able actually to learn representation for roles in addition to words is a challenging question. And then I'm also excited about a specific type of model, sequence-to-sequence model, that maps sentences from different languages and learn representation. And this representation sometimes captures syntax and semantics of English, but the question is to what extent actually these representations are able to capture syntax and semantics of English. Another area that I'm very interested in is the role of attention in children and computers. So when a child starts language learning, the room is these days probably something like the picture you're looking at. There's a lot happening visually in their environment. But they are very good at attending to relevant aspects of their environment and focusing their attention to what is important in this scenario. This attention mechanism actually helps them in learning by reducing the complexity of the situation. Recent neural net models actually started using attention. But in these models, interestingly, although the attention is helping learning or improving the performance, it's actually increasing complexity because it's adding more parameters that the model needs to learn. So there are a few questions that I'm interested to explore. The first question is how similar attention in neural net to the attention that children use. And we can basically think about studying this by looking at eye tracking data from children and comparing that eye tracking data with where the models actually attend to. Another question that I think is harder to answer, but more exciting maybe, is whether we can actually come up with attention mechanisms for neural nets that simplify learning as opposed to making the learning more complicated. And then I want to sum up by kind of say what I started the talk with, that the human language learning is a complex phenomenon that we really do not understand fully. But it seems that a lot of challenges that AI systems face are similar to what people face when they learn a language. And I believe that taking a multidisciplinary approach in studying language learning can benefit both AI and cognitive science with the two directions that I started the talk with. So we can use computer science to learn something about cognitive science of language learning. We can also use cognitive science of human language learning to understand better what the current AI systems lack. And with that, I want to thank my collaborators, and here are a list of other things that I've worked in my PhD and my postdoc. And if you're interested in any of them, please talk to me after the talk or tomorrow. Thank you. Thank you.
Do we learn languages or do we memorize languages?
So what do you mean by memorizing versus learning? How do you
Learning, I mean generalization, right?
Great. So we learn a language with that.
We learn. So then in that case, will deep networks be the right thing to do? So for example, the Google Brain and Google DeepMind people, they showed, so it was Jean Bengio et al., that deep networks are really just memorizing, they're not generalizing.
I don't think that's true. So there are tasks that they're really good at generalizing in. They are very task specific, so you can actually like train a deep net, for example, to do variable in machine translation and generalize to novel instances. The Google Brain actually has this recent paper where it's very cool because they kind of break down all the words to small components, and doing that they do, so the unit is not a word, it's like parts of the words, and doing that they're actually able to generalize to unseen words. So they do generalize a novel task to some extent. It's not that you just memorize.
Well, I guess it depends on what your definition of generalization is. So,
generalization in terms of machine learning.
Right, in terms of training error and testing error.
Right, so in order to be able to actually perform well given unseen data, or like data that has a slightly different distribution than the training data.
I guess we disagree on that. We all have.
Tina, once you memorize probabilities, you actually generalize. That's what all these models do.
No. The reason their models are so big is to memorize. If I have a very big representation, I can just memorize. And most deep networks don't deal with probability. So. But anyway.
So many of them actually you can come up with the objective function of the model and translate it to a probabilistic objective function. The reason that they do perform, the reason that the being deep works is basically the fact that you have a bigger space to search and you have a more flexible model because of that. So you are more likely to find a set of parameters that are able to explain your training data. I agree with you in the sense that what they do is very task specific. But to answer your question about what I explained here, by studying the representation of language, I don't mean language learning is done as a deep net. It's basically this, I think, is the other, the second section of my research where we can look at how people performing language tasks to understand where these models fail. Exactly, basically, if you look at all these steps, we can think about ways that deep nets are not performing similar to humans or are failing, and think about ways we need to fix them. Does that make sense?
I guess I wouldn't even put the way deep nets do it and humans do it in the same sentence, but that's maybe a philosophical question.
Okay. Sure.
Please.
Yeah, so two things. One about this slide, since it's up. So when you try to learn complex grammars, you deal with syntactics. What you do usually with vector space models is words, like words and vector space is semantics, sort of, or word meaning. And this brings me to the other question about one of the early slides about clustering versus context. What is the difference or the relationship between the clusters and context?
Okay, so I understood your second question better, so I'll answer that first. Then you need to tell me more about your first question. So the second question was about what is the relation between the clusters and the context, and in terms of relations they learn.
Because it appeared on the slide as if they complement each other, like they're almost orthogonal and complement each other in your framework. Or maybe to be specific, so how do you do the clustering? Based on what? What are the features? Context.
So the way we did the clustering is using representation that the model learns. That representation is mostly featural, not distributional. So it captures some of the context of the words, because when the words co-occur together, the features of them co-occur together too. So you learn representation for a word that actually assigns some probabilities to the words that it occurs with. But when we look at the context specifically, we are really looking at the distributional statistics. So in these two types of information, usually are good at capturing different types of similarity. One is very good at capturing semantic relatedness. So if you look at context, is often very good at, so if you look at the small data sets, for huge data set, you can do better. But if in smaller contexts, feature representation gives you semantic similarity, context gives you semantic relatedness.
So how the clusters are done again?
How are they created?
Yeah.
So
not based on context.
So let me go back. So the model is actually a traditional process mixture model, if that's the question. But the input to the model is the word representations that we learn. Actually, this is easier. So really what we learn for every word is a vector such as this. And this vector incorporates features that occur with a given word. So this is just an iconic or symbolic vector. But for every word you need, the probability of other words that it occurs with. For example. And then that gives you the probability of each feature for a given word. So comparing these features as vectors, you get a sense of similarity of two words.
So what are the features there?
So the features are the features that actually occur in the scene, and we learn for every word, but features occur with it frequently, per situationally.
Yeah, but in your vector,
so
those aren't featured at the bottom,
sorry?
Your vector for milk there.
So yes, these ignore the icons. It would be something like animate female milk. So these are basically features that we have in the gold standard lexicon. And then your first question I actually missed.
So it was related because when you learn context or the clustering, you learn semantic similarities, and when you try to learn context and grammar, you like the syntactics.
Oh, exactly. So that part
these are not necessarily related at all.
No, so that part of exploration, so that project, the way I envision it is basically you're exploring deep nets representation in their ability to do different things. The first part is really how expressive they are, and you can do that by looking at formal languages.
I like your point at the end about how you have a lot of like complex visual stimuli in your environment, and you attend to all of that, it increases the complexity of the scene. And on the flip side, though, what do you think the role of like a complex word would be in terms of this semantic network? So some ambiguous word rather than an ambiguous environment.
Oh, I see. So if the word has more than one meaning. So
what roles that serve in the?
So there are biases, word learning biases that we know children use, or seems to be actually using. So one specific thing is what is referred to as the mutual exclusivity bias. So this tendency that they have to limit the number of words they associate with a given object. But this is something they actually override. So it seems that at the beginning, they prefer to have one word per each meaning. And then, of course, we're able to learn synonymous words and different types of understanding that one word can have two meanings. But it seems that this is the first assumptions they have, and because of this assumption, actually they reduce the ambiguity of the learning. We did some work where we actually looked at how does different word learning biases impact learning. And in particular, they're very important when the learning is more challenging. For example, for learning low frequency words. If you have high frequency, like words that occur in your data more than 10 times, you can learn in very ambiguous situations. But with low frequency words, having these biases actually guides learning. And it suggests that children will actually use that to learn in challenging situations. So it's something like attention, but in form of a bias that you can think of as a structural assumption about the environment.
So would that inform then what you input to some deep network this learning?
So that project, the way I think we can think about it in sense of like deep nets. So one thing that I guess deep learning researchers talk about is the idea of adding a structure to a deep net, right? And then you can think about this structure as basically normalizing the weights in a given layer. And then you can think about if you're, for example, learning mappings between words and objects, do you want to learn which probability distribution do you want to learn? A conditional over words, a conditional over features, and that type of ideas.
David?
I have a question, which maybe it's a naive question, sort of going between the computational model and how people do it. Now, you had the Hills result on people's recall and patches and so on. And I think roughly stated the idea is that you follow, you have your semantic network and people's recall, roughly speaking, very roughly speaking, follows that semantic network. So like African animals might be more likely to be recalled together.
Right.
And the naive question I have is that when we think about what's actually going on in people's brains, right? I mean, obviously it's not, there's a whole bunch of physiological stuff, neurons going off and so on. How, there's a computational metaphor of like our brain as a computer representing something like the semantic network.
Right.
Is that a fair representation? Are there other ways, other things in the brain that could come out with results like this? Like, how compelling should we find this result as proof?
Right.
This is what people actually do in their own brains.
Right. That's actually a great question. So whenever we talk about computational modeling of language learning, it's in what we refer to as the computational level, not algorithmic level. So I don't think that doesn't help people implement these algorithms. It's just a way to understand what is possible given the input. And I think the main thing that we can learn from this experiment is basically like it's possible to learn a structured representation with minimum computation, and having that structured representation is beneficial because you can simplify your search. And however this is happening in people, it's something that we need to actually have neural data and really not be really able to do it like with this level of computation.
So I guess a couple of related questions. You started to answer the question about ambiguity before, but that actually isn't about, your answer wasn't really about word level ambiguity. So how does the model deal with words that are actually ambiguous, like rose or ball or something like that?
You mean how more than one meaning or more than one sense?
That have complete, well, it's an issue for both cases, but take the sharp, just two independent meanings like rose. right? There's nothing in the model that...
So rose as a name as a flower? Is that
rose as a flower and rose as a verb, right?
Oh, I see, I see.
So there are lots of words in English that have exactly that property.
Right. No, I got it. So we actually cannot deal with having multiple senses by learning one representation the way we do. In order to do that, there are different ways that people have looked at. One is learning multiple representation per senses. So the way I would approach it with this framework is to learn what, like the semantic clustering part, basically, is a good way to think about it. For every usage of a word is actually clustered to a different, can be clustered to a different semantic category depending on the current meaning of the word. And then you can think of those clusters as senses, or word senses. But really, it's a hard problem, and we haven't really addressed that here.
Yeah, so sense ambiguity is going to work out differently than the clear separate cases, right? Sense ambiguity, you're going to end up with a set of features, right, that go with that letter string.
Right.
And for some uses, you're going to get some of the features, and for other uses, you're going to get other features, but they're going to overlap, right? So you can form a cluster out of the senses because, in fact, they're semantically related to each other. They're not all equally related to each other. There's a continuum or something. But cases like rose and ball, where they're completely distinct senses, your learning algorithm is going to end up with just no useful information. It's going to end up with just no particular features associated with that letter string. Because some proportion of the time it's going to get one set, and another proportion of time it's going to get a completely different set.
So the current version does not work, I agree. But you could think of ways where you actually start thinking about two-vector representation. So if you, for example, see a word with a set of different features, so the current meaning is very different from the previous meaning at some stages of the learning. This is basically, again, one of the approaches people frequently use in thinking about multi-type or multi-vector representation in vector space models.
Yeah.
Come up with a different representation.
Yeah, that's fine if you watch that. So then, those sense ambiguities and the sort of true ambiguities, those are usually the reason that you get the triangle inequality and the other issues you're talking about. Right? The reason belt matches with asteroid and it matches with buckle, but the two don't match each other is because it's just completely different meanings of belt.
Yeah. Right. That's a very good question. So one thing we are currently exploring is whether to what extent actually this triangle inequality can be resolved by sense vectors. My intuition is that you're actually getting so there are two things. You can also think about relations among more than two words. And I still think thinking about minimizing distance kind of pushes your representation such that you're not able to learn all the interesting relations. So what I can tell you for now is that my intuition, not really a statistic, is that you actually have a lot of examples of triangle inequality where it's not going to be addressed by thinking about senses. So there are words with similar senses that still you get pairs close to each other, and then the last pair is not very similar. But this is something we're currently thinking about how we can actually explore. Unfortunately, given the data we have, we are not able to easily activate that. But that's a great question.
Yeah.
I guess I'm just curious about when you're modeling how, for example, humans might learn a language if you take into account the ambiguity that's often present in the input stream. So you have the words nicely parsed here, and you can just break them apart by co-occurrence, but oftentimes when humans are learning a language and what words mean, infants aren't even sure what individual words are. And so the input is actually just a stream of sound.
So the word segmentation.
Yeah, and their visual input is often, there's a bunch of things going on, people are acting. And so I guess, do assumptions about kind of the discreteness, I guess, of your different tokens here, does that matter? Or is that something that you think would kind of be informed by this relationship between kind of visual and phonetic input? Or?
So, the stage of word learning that I talk about here is definitely after word segmentation. I think word segmentation starts earlier and is informed by learning word meanings at the same time. So there's this time between actually being able to identify the full words that kids use as information about what they know about previous word meanings to segment the sentence. But it's it's a really different problem that I haven't explored. And about the input, I guess the visual input, it would be thinking about concepts, what is a concept really? So we did some work about that, where again, that kind of relates to word learning biases. So what is an object and how important it is to be able to identify an object and not like learn a word label for it. But the bigger question of like how people are actually able to identify visual, I think that would be needs actually a multimodal study of language and vision, and that would be really interesting.
Well, I guess I was going to say, I mean, I could see for some words, you might learn them at the same time you're still learning how to parse language, like mom or ball are very simple words.
Great. So it's so like when you learn French kids, you know, do not distinguish law and like the articles of the language at the very early on, they just combine them as a word, and that's how they learn it much faster than like the second language learners. Yeah.
I mean, I guess maybe put another way, it seems like you might at different stages have different amounts of information about kind of the associations between these things. And
right, I do agree. Yeah, I think the word segmentation and word learning inform each other.
Well, let me thank again the speaker.
Thank you.